Hello, and in this video I will be solving the question of the day number 93 from the Physics Olympiad Discord server. In this problem we have a thin massive chain lying on a smooth surface, so frictionless, and half of it is submerged in a fluid that has a density 3 times less than the density of the chain. And we are supposed to find out what force needs to be applied to the top end of the chain. The first thing I'm going to do is cut this chain in half and solve this problem in 2 parts. One part for the top end of the chain and one part on the bottom. The method I'll be using is called differential analysis, and I will be finding how the tension varies as a function of theta in this top half of the chain and in the bottom half of the chain. And then at the very end, I'll combine these two together to get the answer. So the first thing I'll do is draw a free body diagram of a small infinitesimal slice of the chain, which I'll represent as a dot. The first thing you notice is that it must have a force going down, which is its weight. We'll call that dmg. And it must have a force going up, t of theta plus d theta. And then it must have a force going down, t of theta. And through some geometry, we can figure out that this angle right here at the bottom, this angle, is equivalent to this angle right here. Now we can write the equation to represent the forces acting on this object in the direction of tension. So we know that t of theta plus g times dm times what looks like cosine theta is equal to t of theta plus d theta. I'm going to move this t of theta on the left side to the right side, so t of theta plus d theta minus t of theta is equal to g cosine of theta times dm. Now we have to figure out what exactly dm is. So let's give this rope some density, lambda, okay? And that means that we know that dm is equal to lambda times some infinitesimal slice of this rope. But that infinitesimal slice of the rope is given by r times d theta. So this is our expression for the small mouth mass of this rope. So now we can write this down again. All I did was I substituted in this dm. Now I will divide it on both sides by d theta. And this part right here should be familiar. This is just the derivative of the tension. So d over d theta of the tension in the top half of the rope is equal to g r times lambda cosine of theta. Multiplying both sides by d theta. And then we take the integral of both sides. On this side, we will be integrating from theta is equal to 0, theta is equal to 90 degrees, or pi over 2 radians, which gives us the tension of the top half of the rope as a function of theta is equal to g r lambda times the integral of cosine theta, d theta, which is sine of theta, plus c. And we'll talk about the c in a second. Now I will erase this work above here so that we can have more room. Alright, so I'm back, and now we're going to be looking at the bottom half of the chain. We'll do the same thing where I draw a free body diagram for the bottom half of the chain. This chain will feel a force t of theta plus d theta going up, and t of theta going down, and some dmg going down, and some fb going up. And this little infinitesimal slice of the chain is at this angle theta, which means that it is equal to this angle right here. Now we can find the expression for the forces acting on the object, or this little slice of the chain, which is T of theta plus d theta plus the buoyant force, which is equal to the buoyant force times the sine of theta, which is equal to T of theta plus G dm sine of theta. Now I want to figure out what the buoyant force is. Archimedes' law states that the buoyant force that this chain will feel is equal to the weight of the water or fluid that displaces it. And we're told that this liquid has a density that is 3 times less than the density of the chain, which means the buoyant force up it must be 1/3 of the weight of any slice of chain that we take. So we can write that as saying FB is equal to 1/3 G times dm. Right? So we plug that in. Plus d theta plus 1/3 G dm sine theta is equal to T of theta plus G dm sine of theta. Subtracting G dm sine of theta from both sides, we get T of theta plus d theta plus 2/3 G sine of theta dm. And we know that dm is equal to density of the chain times the little arc that this little section of chain spans across. So we can plug that in. Like this. Subtracting T of theta from both sides. And now I'm going to divide by d theta on both sides. Which means that the tension at the bottom of the chain, I'm going to relabel this tension as B to represent the bottom half of the chain. D theta, taking the integral of both sides, will yield TB as a function of theta is equal to 2/3 G times lambda R cosine of theta plus C, or this is negative. Now I'm going to erase all this work up here, and we can work on combining these two together. Alright, I'm back, and I drew a free body diagram because now we'll be looking at the little intersection between these two halves of the chain. We know that the chain is supposed to be in static equilibrium, so the force T top and T bottom must be equal, and the force up here is T top at an angle of 0 degrees, theta is equal to 0, and on the bottom the angle is equal to pi over 2 or 90 degrees. And these two must be equal to each other. And we can see that if we set theta equal to 0, this first term will be 0, and we'll be left with C of t. And if we set theta is equal to pi over 2 for the tension at the bottom, we will have the final tension, which is minus 2/3 G R lambda cosine of 0, cosine of pi over 2, plus C B minus the initial state, which is 2/3 G R lambda cosine of pi over 2 plus C B. And hopefully you can see that this part will be equal to 0, and these parts will cancel out, which means C of t is equal to 2/3 G R, and cosine of theta is equal to 1. I'm going to erase this part, and as you can see, I just substituted the value of the constant with what we just calculated. Now it is as simple as solving for t top at pi over 2. G r lambda sine of pi over 2 is equal to 1 plus 2/3 g r, I believe we forgot a lambda here, which is equal to 5/3 g r lambda, and lambda is equal to the total mass of chain divided by pi. So the tension at the top is equal to 5/3 g r m over pi. And then r cancels out. Forgot to put the r there. There's r here because that's the circumference of this, half of the circumference of the circle. Which means the tension at the top is equal to 5/3 mg over pi. 5 and 3 are coprimes. 5 plus 3 is equal to 8, and 8 is the answer to this problem. Thank you for watching this video, and see you next time.